Hello and welcome. This week we are going to start a new topic, new chapter in electronic instruments, and this is on function generator and oscillator circuits. So, other than just ammeter, voltmeter, etc., multimeter, the most important equipment in our lab, in a measurement lab or instrumentation lab, is possibly function generator and oscilloscope. So, I guess these are the two things that we should look into before we finish this course. So, this week we shall study about function generator. So, let us start with a simple function generator, a block diagram. Okay. So, what we will do? We shall take say an integrator and a Smith trigger. So, recall that we have studied both this, the integrator and the Smith trigger, in detail previously. Now, what we will do, we will connect this in a way so that it generates continuously oscillating waveform. Okay. So, the way we will use it is this: the output of the integrator will go to the input of the Smith trigger, and the output of the Smith trigger will go to the input of the integrator. Okay. So, now you see what happens. So, let me just give names like V1, V2, this is the voltage at this point, V2 is the voltage at this point, and this, okay, this is definitely once again V1 because these two are connected. Now, you see that if V1 has some value, definite value, which comes at the input of the integrator, say V1 is constant and say positive, then the output of the integrator will change continuously, will either increase or decrease continuously. Okay. And then what will happen? At one point, this will go or cross the trigger point, upper or lower trigger point of the Smith trigger, and at that point the output of the Smith trigger will change again. Okay. So, let me repeat. Okay. Say okay, the function, how it works. Say at any moment, output of Smith trigger is equal to plus V supply. You know, the output of a Smith trigger is made up of a op amp, that you know, and its output can take only two stable values, either the positive supply voltage of the op amp, this op amp, or the negative supply voltage of this op amp. So, these are the only two possible outputs that a Smith trigger has. Okay. Say at any moment the output of the Smith trigger is plus V supply, and okay, this is equal to V1. So, V1 is plus V supply, and so this will come here. Okay, and therefore, the output here will change continuously. Now, to be realistic, okay, let's draw these two circuits side by side. Integrator. So you know an integrator is made up of an op amp which has a negative feedback coming to its minus terminal. The plus terminal is grounded. This is the output. Okay, so this output is V2, and here we have a resistance, call it R, call this C. Okay, and this voltage is this input V1. So this is the integrator. Now for this integrator, we know the output decreases if the input is positive. Okay, so for this we know V2 is integration of V1t function of time starting from some time t0 to t, let me call it tau, d tau, minus, this is we know, and the constant is here 1 over RC, right? And with this we can add the integration constant, which is the starting value of V2, which is V2 at T0. Okay, so this is how the output changes, and this integrator has this minus sign normally. If you do not like this minus sign, you can also make an integrator. How? Simply you can take a inverting amplifier at the output of this op amp, which will change the sign of the output. Okay, so then you can get rid of this minus sign. Okay, so we so you can go in either direction. You can go with the minus sign there or without the minus sign. So I shall use the minus sign. Okay, in my analysis. So just note this minus sign. Okay, so because of this minus sign, what will happen now? This is positive, this is positive. Okay, if this is positive, then the output will decrease because of this minus sign. Okay, so the output of integrator will decrease continuously with time. Okay, so if V1 is like this, constant, it's a constant, it's as a function of time, it's constant, then here this will decrease starting from some value, I do not know, starting from some positive or negative value. So it will go decreasing like this. This is time. Okay, so it goes down continuously. And so if the input is going down continuously, then at some point, at some moment, okay, this V2t will go below the lower trigger point of the Smith trigger, and which will change the output of the of this Smith trigger. And so the output of the Smith trigger will change. Will change from, so we started with the assumption that this is positive, so it will change from plus V supply to minus V supply, negative. It will become negative. Okay. Now I have made an assumption implicitly, okay, that when this voltage goes down and crosses the lower trigger point, the output of the Smith trigger also changes from positive to negative. So, it also goes down. So, can you recognize which type of Smith trigger we need? Okay, because Smith triggers, we have two types. One is inverting type, another is non-inverting type. Okay. What is an inverting type Smith trigger? It is a Smith trigger whose output increases, goes up, if input decreases below some value. Okay, opposite. And what is this? In this case, output increases, goes up, if the input also goes up and above the upper trigger point. Okay. So, in this scheme, so in this functionality, we have assumed if the input goes down, the output should also go down. That's what I have written. Okay. So, that means this must be a non-inverting type. Okay, because that's what I have assumed here. When the input goes below LTP, output will become negative. Okay, so output will become negative. So that's why we definitely need this type of Smith trigger. Okay. Now, what will happen next? Okay. So, if I just number this A, B, so these are the steps, C, okay, then D. So, now the output is negative. So, V1 is now negative, V1 is now negative, which comes here. And so, what will happen? If a negative input is coming here, this is negative here, so output will now start to decrease. Therefore, output of integrator will start to increase, okay, because of this minus sign. If the input is negative, output goes up. And then what will happen? So, after a while, okay, so now this has gone down. You see, this has gone down. Here it's negative, so this has started to go up. And what will happen? At some point, it will cross the upper trigger point of this Smith trigger. So, after a while, V2 will go above the upper trigger point of Smith trigger, ST in short, okay, and then the output of the Smith trigger will become plus V supply again. So, you see that this way the process will continue. Okay, if this is positive, it comes here. As a result, this voltage starts to drop, and after a while it goes below the lower trigger point. So, output of Smith trigger changes, it becomes negative, and that negative value comes here. Then here the voltage starts to increase, and after a while it will make the output positive, and this way it will cycle forever. So, this way it will cycle forever. Okay. So, now if we look at the voltage at say this point, V1, You see this voltage is going periodically between plus V supply and minus V supply. Okay, so this is a periodic square wave. So this will be a periodic square wave. And if you look at this voltage here, you will also notice that this voltage is periodically sometimes going down, sometimes going up, and then going down, going up, so on. So this will be a periodic triangular wave. Okay, so let me show you some timing diagram. I shall basically repeat my discussion to help you follow better if you haven't. Say this is the time axis, okay, and I shall draw V1 as a function of time. I shall draw also V2 as a function of time. We shall again start our analysis with some assumption that V1 is positive initially. Okay, so initially this voltage is positive. So this is the assumption to start our analysis. Okay, and again we have to take some initial value of V2. Say this is the initial value of V2. We don't know exactly what the value is. Say this could be anything, here, negative, positive. Let's take anything, this one. Okay, and let me mark two lines on this. And these are the voltages corresponding to the upper trigger point of the Smith trigger and the lower trigger point of the Smith trigger. This voltage is nothing but the plus V supply, okay, and similarly I will write minus V supplied down here. Okay, so initially this is positive, this voltage is positive. Now see what happens. So this voltage will this is positive, so this will decrease. Okay, so this will decrease, and the moment it goes or touches this lower trigger point here, so it goes below lower trigger point here, so output will become negative. Okay, and then this stays at the negative value, and therefore this is negative which is coming here, so therefore V2 will start to increase, and V2 is increasing like this. The moment it goes to the upper trigger point here, it will trigger the Smith trigger and make the output positive, and then it will start to go down, because now this is positive, it is coming here, so this will go down, and the moment it comes here, the output will change its sign. This way it will continue forever. Okay, so here we have this square wave, and here we have this triangular wave. Okay, and this is the period. Time period. Now I hope you have followed how it works. Okay, so what's next? Let us now draw the detailed circuit diagram using op amps instead of drawing this block diagram. Okay, so detailed circuit diagram. Let's first draw the Smith trigger. Okay, and we have to draw a non-inverting type Schmidt trigger. Okay, non-inverting type Schmidt trigger. And if you recall, to do a non-inverting Schmidt trigger, we have to start with an inverting amplifier. This is an inverting amplifier. Okay, this is an inverting amplifier. Call it R2, R1, output, input. This is grounded. So this is inverting amplifier. And okay, also let me give power supplies, minus V supply plus V supply. The moment now I change these signs, I will make it minus and plus. This is non-inverting Schmidt trigger. How do I verify this? You don't have to remember, although I remembered it because we discussed it few days back, so it was in my memory, but still you don't have to memorize it. You just verify it. You see, say if I increase this input, if I keep increasing this input, then as an effect this voltage will also go up, and if this voltage is going up, then at some moment it will be more than 0 and this will also go up. So if you keep this going up, this also goes up, and at some point it will become more than 0, it will make this also positive. So output increases with input. Okay, so input output have a similar behavior. So this is non-inverting Schmidt trigger, what we exactly want here. Now let's draw the integrator, which I have already drawn. Capacitor, resistance R, and you know that we have a loop. This loop, this is connected to this is connected to this. So just do it. So this connect you to this. This point is V2, this one, and this you connect here. This is V1. This is also V1. So we can draw easily a complete circuit diagram. Now next interesting question is frequency is how much? So we know the circuit, we know that there is a square wave here, there is a triangular wave here, but what is the frequency? Okay, so what is this time period, say? And just observe that as we have analyzed, the frequency of the square wave and this triangular wave are same. Their time periods are also same. Okay, so let's find what this time period or frequency will be. Okay, so for this V2, you see V2 is increasing from a value of lower trigger point to upper trigger point, LTP to UTP, like a straight line uniformly. So let us calculate how long will it take, will V2 take to grow from LTP to UTP. From that we can find the time period. Okay, so let's write time period, which is same as, I can write, let's call this as T1. So time period is 2 times T1. Now how much is T1? This I can write as the time required for the V2 to go from LTP to UTP, which is same as the change in voltage UTP minus LTP. This is the change in voltage divided by slope of V2, slope of V2, or the rate at which this increases. Okay, this multiplied by 2, this 2. Okay, now this I can write UTP minus LTP. This is also same as the hysteresis band of the Schmidt trigger, 2 divided by slope of V2. Now how much is this slope? of this integrator. If you just go back, you can see this is the equation at which the V2 changes. Okay, so the rate of change of V2 is just this, V1 by RC. Okay, so this will be V1 by RC. So let's write this as 2 RC UTP minus LTP divided by V1. Now how much is V1? See, at this moment V1, the value of V1 is same as minus V supply. Okay, so the value is minus V supply, so the slope will be actually this, you can put a minus here because of this minus sign. So this minus sign, and the value of V1 at this moment, which is same as minus V supply. So this 2 minus cancels, and this will be equal to, okay, let me just write this. So now let's just verify, is my derivation correct? You should always do that, okay, after any derivation. So let's see if this hysteresis gap increases, will the time period increase? Definitely, because V2 has to travel more. Is it inversely proportional to V supply? Yes, it is also correct, because if I have higher value of V supply, or that means this saturation voltages, then the rate of change of V2 will increase and the time period therefore will decrease. This is also fine. Now this RC, okay, you see that if the value of this capacitance is high, then the change of this voltage will be slower. It will need more current, more charge for the same amount of voltage change. So the change will be slow if capacitance is higher. Similarly, if this resistance is high, this current which comes from here to here, that will become smaller. So this voltage, and therefore this voltage will also change at a slower rate. So more the value of R is, the time period will be more, or frequency will be less. So our derivation is correct. Now to complete this, we should put the value of UTP and LTP here. Okay, so let us now find the value of UTP and LTP for this Smith trigger. We did it several times before. You need not remember the result. We will derive again. Okay. Okay. So let's just observe. To find the required voltage at this point, which will change the output. Say at any moment, if say this is negative, this is negative, minus V supply, then let's ask what value of the input will make this Vp equal to 0. That is the crossing point. Okay, so and Vp, we know this is given by from Milliman's theorem. It is V2 R2 plus V, this is VO. Now VO at this moment, we are assuming this is equal to minus V supply. Okay, and so this is multiplied by R1 divided by R1 plus R2. This should be equal to 0 for the output to change, and from this you can ignore. Okay, this will imply the value of required value. So this, the numerator should be 0. So V2 required should be uh, V supply R1 by R2. So this is a very short derivation, quick derivation. I didn't write a lot of things because we did it before. So this is a quick derivation. If you forget, like I forgot, so this is how you can do it. So now let's put the value. So that means this is the value of upper trigger point. Okay, so this is upper trigger point. Similarly, lower trigger point will just be negative of this. So the hysteresis band, now the hysteresis band will be twice of this, twice of V supply R1 by R2, V supply R1 by R2, and this, now this V supply you can cancel. So it is 4RC R1 by R2, 4RC R1 by R2, done. So frequency is how much? Then frequency is 1 over this. So this will be R2 by 4RC R1. Okay, so we can find the frequency in this way. Now let's ask some more interesting question. Like this. How can we change or control the frequency? How can we change or control the frequency? This is the question. Okay, so let me just copy this circuit for ready reference. And let me also put this in front. So basically this is a function generator. You see, this is actually a function generator, right? It generates two functions, one square wave here and a triangular wave here. Okay, so this is a function generator. It generates two functions, and we want to now change the frequency. Okay, I mean in a function generator in our lab, we have this control to change frequency, amplitude, etc. So let's ask, how can we modify this circuit so that the frequency can be changed? Okay, so the answer is simple. So this is the expression of frequency. So that means what we can do, we can change either of any of this R2, R1, RC, all of them will change the frequency. So we can make this variable, we can make this variable, similarly we can make this or this variable, all of them will change frequency. Okay, so we can change R or C or R1 or R2. Okay, we may not like to change R1 and R2 because then the hysteresis band of this Smith trigger will change, and it should not be too low. The hysteresis band should not be too low, then noise may create problem. So, but anyway, we can at least change these R, C, and there is another thing we can do. Okay, another option, we can actually change the voltage supply here. Instead of connecting this output directly here, what we can do, let's take a potential divider. Like this, and this you feed here. Okay. So, now the voltage that actually comes here is not the entire V supply, but a fraction of it. Okay. So, therefore, say suppose if I bring it down, then this voltage which is actually here is lower. Therefore, the rate of change of this voltage will also be slower. So, frequency will decrease, go down. Okay. So, frequency will decrease if we lower this slider. Okay. And how exactly that will affect? In this derivation, we wrote, we wrote V1 by RC is the slope, and we wrote V1 is equal to minus V supply. Okay. But it may not be so, it can be a factor, get multiplied by a factor k, where k is determined by this potential divider. Okay. This k is the factor or fraction of this voltage which actually gets there. Okay. And therefore, this k will be everywhere. Here, and to be more precise, I will also do another small modification to keep this equation perfect. I shall put a small buffer. Okay. So, this is a symbol of a buffer which could be just this op amp. Okay. Direct feedback. So, this is a buffer. Okay. So, this thing I am for to save space I am just drawing like this. So, this is a 1:1. So, whatever is this voltage, this goes there. It copies the input to the output. Okay, right, but it does not take any current. This current is 0. The current here will be 0. So, this will ensure that the voltage which actually goes there is really the ratio between this resistance and this resistance. Otherwise, if some current is flowing here, the voltage will actually not, this voltage, call it V1, and this V1 is equal to, this is, okay, call this, okay, then call this V1 prime. This is V1. So, V1 prime is this V1 multiplied by, if this part is R1 and this lower part is R2, then this is equal to R2 by R1 plus R2. This equation will be exactly true if I have a buffer here. Okay. And if I do not have a buffer, then some current will be drawn, and then this equation will not be exactly true. But yet it can control the this voltage and the frequency. Okay. So, here k is this R2 by R1 plus R2. Okay. So, this is how these are the few methods with which we can control the frequency. Right? Yes. So, we can change this resistance, capacitance, etc., or we can change this voltage applied to the input of the integrator. Now, let us ask another interesting question. Can we also generate sine wave? Because we already have triangular wave here and square wave here, can we also generate sine wave? Because in our laboratory our function generators always have sine wave other than the triangular wave and square wave. So, can we also generate by modifying this circuit or adding something to this circuit? Okay. So, let us see how we can do that. So, for that, let us consider that I have a voltage and a potential divider. Okay. So, this is say a input voltage V I, and this is a potential divider, this is the output. And now if I have a triangular wave here, okay, Vi is a triangular wave, then how will this Vo output be? It will also be triangular wave, right? Because I mean output is simply if I call this R1, if I call this R2, now this is simply Vi multiplied by R1 by R1 plus R2. So, if this is triangular, this will also be triangular, quite natural, with a reduced amplitude, right? Okay. Now, I shall modify this circuit. What I shall do is this, say I'll connect a resistance and a diode and here I will give say a voltage, call it VT1, right. So, now and this VT1 has a value which is positive, plus VT1. Okay. So, this is a positive voltage which I will connect, and its value is lower than the amplitude of this. Okay. Which was the output before having this part. Okay. So, if this height is something VH, this height is VH, then this VT1 is below or lower than VH. So, this is what I shall connect. Now, you observe that if Vi is increasing slowly from the value of 0, if Vi T is increasing from 0, then this Vo will also increase. Okay. So, this voltage Vo, which is also the same voltage here, will also increase, but initially it is 0. Okay. So, initially this is at 0 voltage and this is at a positive voltage. So, this diode is reverse biased. So, initially Vo is less than VT1. So, call this D1. Okay. So, D1 or call this DL1. So, DL1 is reverse bias. So, effectively this part is not connected. So, effectively this branch I mean, what can you call this branch 1. Effectively, branch 1 is not connected or is not there. So if this branch is not there, then how will the output change? It will change ignoring this branch. So as the input increases, output also increases. So let's draw. This is time. Okay, so this is VIT, which is increasing from 0 . Okay, and so VO will be therefore also increasing, but at a slower rate because of this potential divider. If R1 is equal to R2, then this slope will be half, output will be half of input. So this is supposed to increase like this, and it will increase like this initially. And say this height represents the value VT1 plus VT1. So until this output goes to this level, so this voltage is lower, this is higher, this is reverse bias, effectively this branch is not there. So okay, the output will just go increasing, assuming this is only this part is there, this part is not there, so it will go like this, no problem. But at this moment, at this point, something different will happen. What will happen after this point? After this point, this diode will be on, right? So this diode will be on, forward biased, okay? So call this time T1, okay? And let me just copy it. So at T1, this diode will be on, DL1 will be on, and therefore this branch is no longer ignorable. I have to take care of it. Okay, so what I have to do, to find this voltage, I have to consider this, okay, and call this R3. Okay, therefore, if Vi increases from this point, call this current I, a fraction of this current I will flow through R3. So previously, the entire I was flowing through R1. Therefore, this voltage was increasing quite rapidly. Now, a part of I1 will branch through this, and therefore, this current which goes through R1 is lower, smaller. Therefore, this voltage will not increase as fast as before. If this voltage increases by some amount, or if this current increases by some amount, previously this voltage was increasing by, if this voltage was, this current was increasing by delta I, then this voltage across here, this was increasing by delta I times R1. but now it will increase by an amount less than delta I R1, because part of delta I will go through this. So this voltage will now not going to increase as fast as before. Okay, the same thing I can explain in another way. So now onwards, you can consider these two resistances are in parallel. Any delta change in this voltage, okay, if this voltage changes by delta Vi, then the voltage that will change at this point or across R1 will be delta Vi multiplied by a fraction. What fraction? It is not R1 plus R2 by and R1. It is not this. Instead, it will be R1 parallel R3 divided by R1 parallel R3 plus R2. So you see these two resistances are in parallel, and therefore the effective resistance is lower, because two resistances in parallel is a lower resistance equivalently. So this resistance is now lower. So therefore the fraction of the voltage that comes here will now be lower. So if this increases by delta Vi, this voltage will now increase only by this amount. So this, therefore, the voltage will not increase as fast as it was increasing here, but it will increase at a slower rate, like this. It was increasing like this, and now it will increase like this at a slower rate. Okay. So let me write, increase I will flow through, so a part of I will flow through R3, therefore remaining part only remaining part goes through R1, and so the rate of change or increase, rate of increase of this voltage, which is same as VO, will become slower. You can also think it in this way. You can also think that after T1 time, R1 and R3 are effectively in parallel. Therefore, the rate of change of VO will be slower. So VO will change relatively slowly. Okay, so I hope I have convinced you this fact that now, because of this arrangement, this voltage diode and this resistance, the voltage was initially increasing fast when the diode was off, but now after this moment the voltage will increase slowly. Okay, and similarly, you know, when the input is decreasing, you know, the output will also decrease in a similar way. So the here and these two parts should be same, because I mean, like here the input, whatever is the value of input at this point, the value of input at this point is also same. Okay, so it will decrease in a similar way, and up to this diode DL1 is on. After this, when this voltage output goes below this threshold, so now this diode will be off again. If I call this time T2, okay, after T2, DL1 will be off again. So, you can ignore branch 1, this branch, and so here DL1 off, here also DL1 off. So, now this is not there, R3 is not there in parallel with R1, R1 is there alone effectively. So, this will now decrease faster, just like this, symmetrically. Okay. And then, okay, what will happen after this? This will continue like this, because even if the voltage goes below 0, negative, so this is negative, this is positive, this branch is always off. So, this has no effect at all. So, this will have no effect at all. So, therefore, on this side it will go following this higher slope. Okay. And now what I will do is this, I will put another diode. So, what I shall do, I shall put another symmetrical arrangement. I'll put a diode here, and I'm actually thinking what to do. Okay, you can also think with me. So, this side I'll put minus VT1, so that when this voltage, this value is minus VT1, if this voltage goes below minus VT1, this part should become active. Okay. So, if this is lower, if this side goes lower, then this diode should be on. So, I'll put the diode in this way. Do not memorize, always think what to do. So, now we can analyze. You see, when this voltage is going down, and if it goes below this threshold VT1, this is VT1 and this is negative. Okay. If this goes below this value, then this is lower, this is higher, and this diode will be on. This I will take as R3, and then once again this R3 will come in parallel with R1 effectively, and therefore, it will now go slower like this, just as it was here. Okay. I'll call this DR R1, L for left, R for right. Okay. So, here DR1 is on and DR1 is off throughout. DR1 is off throughout in this positive half as well as in this part of the negative half. And in the negative half throughout, DL1 is off, because this is negative, this is positive, so it's off. So, effectively what we have done, let me tell you, effectively we have given a triangular wave as an input to this circuit, and the output is this, which is not triangular, but which is like a piecewise linear function, and this is not triangular, but it is more somewhat closer to a sine wave. Okay? This is somewhat closer to a sine wave. So, in this part the rate of change is slower. So, like a sine wave, sine wave initially increases faster, then slower, like this. So, this is a sine wave. So, this is an approximate sine wave. So, this is an approximate sine wave. You may not be happy, this is not very close to a sine wave, But if you want to make it more closer to a sine wave, I can just extend this idea. How? You see, what I will do, let me also erase this here. What I shall do, I will take more such diodes, such arrangements. So let me take one more. Call this this voltage that I will apply here is VT2. Okay, so I have to apply this voltage like here as well. So I have to take a battery or something, and I have to apply this voltage. Similarly, here also I have to apply this voltage. Okay. Similarly, here also you have to apply this voltage. This is negative. Okay. Now, what I will do, I will take VT2 greater than VT1. Okay. This you can take R3, R4, or you can take them equal if you like. And I will take another similar branch in the opposite direction. This will be also R4, diode, this is VT2 plus, so this I will take minus VT2, symmetric arrangement, but more number of branches. So now what will happen is this. Let me clean it up. Say the normal, I mean, if these branches were not there, in the absence of these branches, VO increases like this. Okay, so this is the pattern in the absence of the branches, I mean these branches. If this was the volt pattern of the output VO, okay, then on this I will draw these levels, plus VT1 minus VT1. Similarly, here I shall draw VT2 plus, and here minus VT2. Initially, say if this voltage is increasing from 0, this is also increasing from 0. So this point is at 0, all these are positive. So all these diodes are reverse biased, and then these resistances are not effectively there because these branches are open. Now this voltage will increase initially, so it will increase like this up to this point, and at this point this voltage will be more than this. So this diode will be forward biased, and this R3 will come in parallel with R1. So, therefore, the rate of increase of voltage will be slower, and it will go like this. Okay. And at this moment, this potential will be even higher than this. So, this diode will also be on. So, therefore, these two are in parallel with this. So, effective resistance here is much lower. So, then this will go down even slowly. Okay. And now, when the input comes down, so we will have similar opposite pattern. It initially goes down slowly, then at a faster rate, and then at a like this, then at a faster rate like this, and then even faster rate. So, this is an better approximate sine wave. Similarly, on the negative side, if you do the analysis on your own, I am not doing it, I request you, please do it. On this side, you will also find initially it will go down fast, then it will go down slower, and then even slower, and like this. Okay, my drawing is not good, but you do the analysis on your own. I hope you can do it. Okay, I believe you can do it. So, this is a better approximation, better piecewise approximation. Okay, approximation of sine wave. If you need even better, take more stages, 3, 4, as many as you want. So, this way we can generate approximately sine wave. Okay, and this is not smooth, but then if you have studied filters, anything, you can give this input to a filter, then these corners will be even smoothed, and so you can generate a better sine wave. And so, what you can do in our function generator, you just see we had a triangular wave generator. So, what you can do, you can take this triangular wave, connect that to this circuit, which generates a piecewise linear sine wave, approximate sine wave, or here, and you can get a sine wave, and then you can filter it if you like. Okay. So, then today what we have studied one function generator, which is made up of just a Smith trigger. We studied before integrator, connect them in a loop. We did discuss in detail exactly how to do it, detailed diagram, how to remember things, or how to better derive things on spot, not to remember, and then how to get a approximate sine wave from this. So, now we have a function generator which generates triangular wave, square wave, as well as sine wave. We can use it in our lab. Thank you.